Welcome to lecture number 6 of Elements of Machine Learning, season 2022-2023. So, well, right now, officially on my calendar, it's still Friday, the 25th of November. However, officially this lecture is planned for next week, December 1st. So, well, whenever you're watching this, but for now, I'm just going to say welcome. Good. In the last 2 weeks, we've been talking about classification. In the 2 weeks before that, we've been talking about regression. And in those 4 weeks, we've been completely ignoring the fact that, well, in the end, we don't really care about the fact that we can obtain models that predict well on training data. Actually, what we're interested in is models that are going to be behaving very well, they're going to have high accuracy when we run them in the wild. They should have a high test error on unseen data. So I mentioned a few times that just focusing on training data is stupid. Today is the moment where we're finally going to learn how we actually can estimate properly, statistically sound, what is the expected testing error for a method. Okay, good. So, well, let's get started. We should always test in order to guesstimate how good is the generalization of our method on different data than we trained on. Because otherwise, it's all make-believe. Now, the most basic approach you can think of to do so is take the data that you got, divide it randomly into 2, and, well, fit your method on the one half, and then use the second half to see how far off your estimates are. In that sense, your method will not have a chance, or relatively little chance, on overfitting on the testing data, right? Which we do have when we evaluate on the training data alone. So if we put it in a figure, we have this. We have all data that we're given. We somehow randomize the order, right? So this is 1, 2, 3, all the way up to n, indicators for the records. And here I split it half-half, and it starts with record 7, then 22, then 13, and so on and so forth. And the second half, well, the last record is number 91, just to indicate that it has been randomized. How should we split? Well, 50-50, whatnot, whatever you think is a good split. As long as we keep the training and testing data separate. Why do we randomize, you may ask? Well, give it 2 seconds of thought. Indeed. The moment that we do not randomize, there might be some correlation in the order of the training data that we're given, where maybe the first half is easy and the second half is hard. Perhaps, I don't know, I mean, these are the patients that are very clearly completely healthy, and the second half are the ones where, well, there's actually a few very nasty cases that you would like to pick up. Well, quite obviously, if we do not randomize, then the method will not be able to catch this. Good. That's why we randomize. Let me give an example. Let's go back to one of the examples we've seen before, the miles per gallon example, the auto example, where here we have the scatter plot again. This is horsepower. Here we have miles per gallon, lots of data. If we fit a linear regressor, in this particular case, we get this beautiful ochre colored line. If we fit a polynomial of the second degree, then we get the pretty neat blue line. And if we fit a polynomial of degree 5, we get this somewhat overly squiggly and clearly completely going out of bounds there, squiggle. It's the 5th degree. So by looking at this in 2D, kind of already see, we can kind of feel that degree 2, maybe degree 3 is going to be good. Degree 1 is too little. Degree 5 is too much. Degree 42, I mean, let's not even talk about that. Okay, now, what we should be doing, of course, is evaluating how well these polynomials that we fitted perform on testing data. So in this particular case, what we have done is that we evaluate the validation error on a 50-50 split. We have as much testing data as we had training data. And well, we evaluate the mean squared error now on the validation set. Validation is also another word for test. And as you can see, well, for degree 1, we have a pretty bad MSE. Degree 2 is pretty good. And then, well, yeah, actually stays pretty good. That's okay, fine. Now, that was just one split, right? Once we splitted the data into two halves, what if we do it another time? Are we going to get a different result? Is it stable? What is the variability of this statistic? Well, here we did it 10 times. And as you can see, for each of these lines, well, the test errors vary quite wildly, right? For these orange ones, the estimated test error for the degree 1 polynomial is close to 29, whereas for this lime-colored one, it's 21 and a little bit. That's quite a big difference. So, which one should we now trust? Well, the good thing is, of course, if we could run this multiple times, we can average out the variance, right? So there is a high variability, but if we do this many times, then we can average this out. That is good. What otherwise do we observe? We observe that quadratic is clearly necessary, and beyond that, there's not so much benefit. However, if we would solely pick the best model, in this case, the degree of the polynomial, out of the ones that achieve the minimum error, then it really depends on which split we have, right? So for the dark orange one, would be degree 2, fantastic. For this one, we would be degree 7, not so great. For the lime one, it's also degree 7. Okay, so we need perhaps another principle to figure out what is truly the best model. What is the complexity of the best model? What is the true test error? Yeah. Okay, now that aside, what is now, in a way, the problem, or what is the origin of that we have such a high variance here? Well, by splitting the data half-half, we of course massively decrease the training set, the size of the training set. So our method has just little or less chance to figure out what is correct. And as a result, the test error may be overestimated. Good. Now, if we say that 50-50, we have too little data for the training set, what can we do to avoid that? Let's use almost all of the data for the training set. Well, what is the largest amount of training data we can use while still having some data for a test set? Quite simple, we keep one data point aside. That's the key idea of what we call leave one out cross-validation. So what we now have is a training set that is as large as can be. So there is very little bias there, or as little bias as we can afford, right? However, we only have one point to test on. So if we're lucky, then perfect, but it's kind of hit or miss. So we'll have a very high variance in our error estimates. Now again, averaging to the rescue. If we simply repeat this process for every data point, that is, not only, so in this particular case, I train on data points 2 up to 47, or 4, up till n, actually, up till n. And I evaluate on data point 1. But I can also test on data points 1 till n, and except for data point 2, which I evaluate upon, and so on and so forth. I always leave one data point out. I always train with the maximum amount of data. And I simply, well, the mean squared error for one data point is simply the squared difference between the output, the expected output, and the true output. And if we now just take the average over that, then we have the leave one out cross-validation estimate. So that's neat, right? We avoided the whole bias thing on the training side. We can filter out the variance on the testing side. Plus, not unimportant, unlike the test train split that we had in the validation set approach, the process is now deterministic. No matter how often we repeat it, we're going to get the same estimate. It doesn't depend on random initialization. That is very nice. That is very nice. You want to avoid the situation where you say, oh my God, this model is so good. And then your colleague runs it and like, well, I think it's kind of meh because look at the, so with leave one out cross-validation, you avoid this. Let's have a look at how good these estimates are and how do they vary now compared to the validation set approach. I brought this figure. Well, we have first degree of polynomial. This is essentially the plot that we just saw, right? But then averaged out again. This is the validation set approach, 50-50. If I now compare this to the leave one out approach, which I have over here, then you see that the estimates are actually quite similar. You might, perhaps you'll be overinterpreting, we'll see later, you might even see an improved behavior because look, this drops, and then here at the end, it climbs up again. So around the time when we're really overfitting, much too high a degree of polynomial, it goes up again. Maybe we're seeing ghosts. We'll figure this out in a bit. Now, the nice thing is that for least squares and polynomial regression, we have a quite handy formula to compute in one go the leave one out cross-validation result. We have, it's the difference between the predicted versus the actual label, and we normalize this by 1 minus the HI. What is HI again? Remember from lecture 3, when we spoke about which points can be most detrimental, or how can you make points most detrimental to your linear regression? Well, those are the points with high leverage. They have a very high influence on your regression coefficients, right? These were the elements in the Hessian, you might also remember. Well, those values we can simply determine for each data point, right? Look up in lecture 3, and I think that is also chapter 3 in the book at the top of my head. That allows us to essentially factor out the influence of data point xi from the entire thing, which gives us, after we fitted our linear regressor or polynomial regressor, in one go the cross-validation result. So we don't need to do any additional work. That is pretty neat. Now, is this now ideal? Is this now ideal? I mean, suppose that we cannot use a trick like this, right? And even if we don't, now we need to compute everything, this might also be a bit too much work. Perhaps we're lazy. Do we really need to train on, basically, if we have n data points, n minus 1 times, that sounds like a lot of work. Can't we shrink that a little bit? Well, that is the core idea of k-fold cross-validation, where the idea is very similar as what we've just seen. Rather than that we leave just one data point out for testing and training on the rest, we leave a whole bunch of them apart. We call this a fold. And what we do is that we divide the data into k equisized or as equisized as possible folds. So in this particular case, there are 5, after first randomizing the order of the data. Why? Okay, this time I'm going to give you 1 second because we already determined this for the validations. So what we now do is that we keep one of these folds, one of these chunks of data aside for testing, we train on the rest, and we get an error estimate. We do it again, the whole training, but now on training on fold 1, skipping 2, 3 up to whatever, evaluating on fold 2, and so on and so forth. So we get k error estimates. Now the final estimate of the test error over all of the data is simply the average of those, right? That's what we have over here. Now, in practice, we can choose k whichever low or high we like. But if we choose k as n minus 1, then we actually have leave one out cross-validation. We're doing a lot of work and we just have reinvented something we already knew. In practice, we use fewer folds. Typically, we use something like 5, 10. Personally, I'm a big fan of 10, but 5 is also fine. Now, one of the advantages of cross-validation is that it's much more efficient than leave one out. However, it also has a higher bias because, well, you have less training data. So that we don't maximize the training data as much as we do and leave one out. So there is a bit of a trade-off between the bias and the value of k, the other way around, if you wish. So the higher the value of k, the lower the bias, because we have more training data. Good. Let's see how this works, how this compares to the plots that we've seen already so far for validation set. Here it is again. Let me superimpose the error estimates for leave one out cross-validation. And now let's overimpose 10-fold cross-validation. I don't give you just one line. I don't just give you a green line, but I give you a whole bunch of them. Why? Note that unlike leave one out cross-validation, the process is now not deterministic. I randomized the order of the data set to begin with. And under different randomizations, with the same number of folds, I will get different training sets, respectively test sets. So that means I also get different error estimates. As you can see, the variance of these, well, it's not so bad. Not so bad, right? Definitely not as bad as the 50-50 validation set that we saw earlier, right? This is pretty decent. However, there is still some variance, right? For these 10. Now, if we want to reduce, get rid as much as we can of the variance of these cross-validated estimates, what we should do is repeat cross-validation multiple times. So very often in the literature, if you can afford it, validation time-wise, again, bye-bye for deep learning. But if you do linear regression or you do something slightly more involved, but nothing too extreme, I recommend you to use 10-fold cross-validation if your data set is large enough, and to repeat this 10 times under different permutations. If you don't differently permute, you can just do it once, then there's no difference, obviously. And you report the average of these 10 independent cross-validation runs. And that is your final result. Then we really squeeze the data as dry as we can in terms of evaluating how good a method is going to be. Okay, let me see. I need my bottle. Empty. That's better. So, let's continue. Let's see if this works. Let's start with an example on data that's almost linear. Hey, you know this data set. Yes, I'm going to reuse it time and time again. So what we have here, we have an almost linear data set. We fitted different models, linear, smooth, rugged, splines, whatnot. For all of those, we can evaluate what is the degree of freedom, how flexible are they? And what we can now see is that the true function as a certain, this is the test error of the true function, sorry. Now, if we use leave one out cross-validation, we get the red dotted line. It's over here. And the 10-fold cross-validation line, which saves a lot of computation time, as you can see, well, yeah, it's almost as good as leave one out, right? That is pretty neat. What else do we observe? We observe that in this part of the game, well, the estimates are pretty darn good. So they underestimate the error slightly, but here, okay, here they go off key, right? There is a huge difference in the true error versus the estimated error. That's a tendency that cross-validation has in general. Okay, let's go to a slightly less linear example. So now we have the moderate nonlinear example. I'm not going to plot the data again, but hopefully you remember. So this is the true function, as you can see. Okay, if we use the true function, this is the error, and this is the minimum. If we now look at what are the estimates of leave one out and 10-fold cross-validation, well, we see that once again, it's almost potato. We can use either of the two. They're equally good or bad. Your call, is this good or bad? If we're interested in the true test error, estimating this through cross-validation, you see that, hey, cross-validation underestimates the test error. We already saw this with the linear case, but here it's much more clear. And then for higher degrees, right, if we essentially have an overcomplicated method, it tends to overestimate again. Here the damage is a little bit less than perhaps here, but so is cross-validation perfect? No, it's not. But it is one of the most powerful tools we have. Let me show you a third example. Third example is for highly nonlinear data. And all of a sudden, you see that actually this is pretty much the sweet spot, right? So we underestimate, sure, for two simple models, but these are so far away from the true minimum that who cares? Sure, we overestimate if it's even more high degree, but in general, it's pretty much spot on. Cross-validation is one of the most powerful ideas that came out of machine learning, statistics, data mining, whatnot, whatever, how you want to call the field. It is a superpower. It's a superpower. It's still in many other engineering fields, they either don't know about it or they have only just learned about it. That may be a bit surprising because, come on, it's so simple, but yeah. Now, one of the problems is that you need to be able to train your method k times if you want to use k-fold cross-validation. Of course, if your method is particularly expensive to train, you may not want to do that. right? Even if you are aware that cross-validation exists. Okay. Now, let's follow up on that thought a little bit, because not only are we often interested in the test error, we are even more often interested in the location of the minimum. Like here, this is an almost perfect estimate, right? This is the true minimum. This is the best possible flexibility. This is the leave one out, and this is the cross-validated estimate. So there it's pretty good. Why? Because we want to know what is the complexity, what is the order, what is the flexibility of the best possible model. Because if we have that, we add more data, okay, then we can just fit the parameters better. We can get the test error perhaps even down, but we don't want to be using this model over here, right? A model with degree 3 or 4, essentially no matter how much data we throw at it, it will never be able to capture the true essence of the data. I mean, it's way too biased. Whereas if we have an overcomplicated model, it's way too variable. So this is what cross-validation is really good for. Now, still a bit of a problem. The test errors, they vary. We saw that if you randomize your data, it's slightly different. So sometimes the minimum is not really that clear. We saw also, I mean, this picture is beautiful, but in the previous figures I showed you, when I was explaining cross-validation still, that it sort of dipped and then, yeah, but where's now the minimum? The minimum sometimes is here, sometimes it's here, sometimes it's there. Who knows, right? Well, by having multiple independent runs, we can average this out, and maybe the minimum starts to become more apparent. But often you'll see that there's many different models that have almost the same error. It's a little bit what we have over here, right? In this plateau, which model should you choose? Should we choose this one, the true? If this is the estimate, right? We have either the orange or the red estimate. Should we use this one, this model with degree 20, or with degree, well, let's say 6? They all have the same test error. Well, you all know of Occam's razor, right? If you have two explanations or two theories that do perform equally well, go for the simplest one, right? Sort of a gut feeling is also like the KISS principle, keep it simple and stupid. Not simpler than it should be, but definitely not more overcomplicated, because then just too many moving parts, right? Well, with that in mind, we can also choose what is the best complexity of the model using cross-validation. Namely, we choose the simplest model that is one standard error of the optimum. Okay, well, that is something we can relatively easily evaluate, standard error, by just repeating it one number of times. The standard error, no problem. And then, well, here we have the minimum, right? One of these stars. And now we just try to find that model that has, well, it is the lowest complexity, but it's still within one standard error. So perhaps the 5 or 6 one, and yeah, pretty decent, pretty decent. But you will see good performance in practice. It does tend, especially for highly nonlinear cases, as here, to slightly underfit, right? We have a slightly too simple model, but in other cases it may overfit. But as a rule of thumb, it does very well. Well, doesn't just work for regression models. As we've just seen, we can also do subset selection. Which subset of variables do we want to include in a model? We can do it for classification. We can use cross-validation actually to evaluate any parameter, any choice. It is really a superpower. When I said that, it was no joke or anything. We have now a way to determine what is the optimal value of any parameter. In subset selection, here we have, so what is now the minimum? Minimum is probably here. What is now standard error? Oh, there we have it. Okay. Yeah, subset of 2. I forgot which example this is now exactly, but just to show that we choose subset size 2 rather than 3, 4, 5, 6, and so on and so forth. Very nice, very good. So normally, this would be an in-person lecture. I would say, are there any questions? Are there any doubts? I mean, how simple or can we use it for this or that? Okay, right now, given that it's pre-recorded, I'm just going to skip that part. We'll see either in the tutorial or in the next in-person lecture. We can discuss it a bit further. Good. Let's look at cross-validation now through the lens of our good friend bias-variance trade-off, right? Lecture 1 calling again. So as you see, in EML, everything is connected. K-fold cross-validation tends, in practice, to give more accurate error estimates than leave one out cross-validation. It's often by bias-variance trade-off. If we increase the relative size of the training set, of course, this reduces bias. That's what we have in leave one out, but it increases variance. That's what we have in leave one out, right? So cross-validation finds a slightly better balance there. There's another problem. If we look at leave one out cross-validation and we look at two different, say, values of the test area we compute. So in the one case, we might be training on data point 1 or testing on data point 1. And in the other case, we're testing on data point 2. And we're training on, in both cases, the rest of the data. There is an enormous overlap between this training data. That means that the models we discover in these two cases are going to be pretty much the same, right? That is, the estimates, they're going to be extremely highly correlated. So the variance bites us in the back basically all the time, right? So the bias on the one hand, in k-fold cross-validation, by evaluating on the entire chunks that we then do not train on, we have less overlap in the training data. And as a result, we have the potential of slightly different models, and that creates less correlated, more little correlated estimates. Now we can estimate the variance of the average of the outcomes of k identically distributed events with a correlation rho, each with a variation of sigma squared as what is given here. Okay, let's walk it through again. The variance of the average of the error estimates, that's what we're interested in, of k identically distributed event, over different folds, which because we randomized each of these folds, we can assume to be identically distributed, right? There is no reason, especially if we repeated this numerous times, that there is going to be a very strong correlation between selecting hard data points here, and these are the easier data points, identically distributed. In this particular case, you may assume to be true. They have a correlation rho, that is the overlap in the data sets, and well, the variance in the estimates is then sigma squared. So this is what we have here. This is the expected, you could say, or the variance of the average of those things. If you work this out, the more correlated it is, the higher the correlation here, well, the bigger the variance is going to be. So that is what goes wrong with leave one out cross-validation, if you would like to call it that, and what goes right with k-fold cross-validation. Once again, k-fold cross-validation is really like it's one of those brilliant ideas that many people know now about it, but very few people realize the brilliance behind it, why it works so nicely. Good. Let's look at it in action. How can we use it? So an example, but this time we're going to look at classification. Here we have it. I have 4 examples for you where I have data on which I'm going to be fitting individually 4 different models. On the left, all the way on the left, of logistic regression with polynomial of degree 1, so it's really linear logistic regression. The second one, I have a polynomial of degree 2 that I fitted. So I have quadratic logistic regression, then I have cubic, and then I have quartic. I could have had more, but couldn't be bothered. This is essentially the formulas that I've been fitting, right? On the left-hand side here, the logarithm of the probability of the one class over the one minus probability is simply, here we have just a linear model. For the quadratic, it looks like this. For the cubic, it looks like this, and then I stopped because otherwise the slide overflowed. And for the quartic, there we go up to the power 4, and also for the second x, of course, but let's save a bit of pixels here. But now for each of these, we can now use cross-validation to evaluate test error. Just by gut feeling, if we go from left to right, you would expect that the first one, well, that's a pretty bad fit, right? I mean, the dashed line is once again the Bayes optimal decision boundary. The quadratic is better than the linear, but yeah. The cubic, not bad, right? Not perfect, but I mean, it fits the data quite well, right? I mean, there's not so much evidence that it here needs to take this weird jump, right? And same thing here. Why would it take off here? I mean, this is actually pretty decent. And the quartic, well, I'm pretty sure if I would give you the cubic and the quartic side by side in an exam, and I would ask you, okay, what are the differences? Some of you would say they're the same picture. You would be almost right, almost. Let's look at the test errors. From left to right, what do we have? We have a test error of 0.201, 197, indeed, not much better. For the cubic, 0.16, now we're talking, and the quartic, 0.162, right? Okay, so those are very close to one another, and this, well, difference in a thousandth, that may be just to the variance, right? So we don't know for certain if cubic or quartic, which is now really, really better. But if we go in this rule of the simplest model within one standard error, then we would go for the cubic one. If we compare this test error, the true test error, or the test error, the 1016, to the true test error, which we know because this data is synthetic, and that's why we can determine the base optimal decision line, and then we can see what error would that give. That will be 0.11. So we're still a bit off, but it's much better than just a linear in this particular case. Okay, good. Now let's continue. What can we use this for? Here we have essentially what we just saw, but then slightly differently put. Error rates. This is the order of the polynomial. So I showed you basically up till here. And we use cross-validation to estimate these test errors. What do we have? We have in blue, we have the training error, right? It's shown here on the right. We have in black, we have the tenfold cross-validation error. And what you see is that whereas the training error, essentially, well, it dips and it goes up and then it dips. So there we would have chosen a highly overfit model. In cross-validation, well, we have more of a U shape in this particular case with a nice minimum that we would choose. And if we compare this to the shape of the true test error, then you see that, well, we are slightly underestimating the test error, but not massively so. And if we stick within this rule of a standard error, then there's a big chance we would have indeed chosen the model of the right complexity. That is, again, simplicity strikes. If on the right-hand side, we do exactly the same thing, but now for k nearest neighbor-based classification, where we vary the value of k from all of the data to just one data point. K is 1, right, on the right-hand side. And as you can see, the training error, well, the lower the value of k, the more we overfit. Then it goes down. Also notice, by the way, that my little rant last week on bad x-axis plots, well, here we go, right? Because it now looks oh, it's below 0. No, it's not. It's just you don't show it anymore. Anyway, blue really underestimates the test error. Cross-validation also underestimates, but as you see, the minimum is very close to the minimum of the true test error. So what does that mean, boys and girls, and anybody else? This means that cross-validation, no, it does not give you the exact true test error. It can't. In the limit, if we have infinite data, okay, then sure, then we can. But then we can also do the split 50-50 because infinite by half is still infinite, so that's all good. But it does give us a pretty darn good estimate. And it can tell us what is the complexity, the right complexity of the model. And once we have that, the moment we get more data, we just train it better and better, and then slowly but surely we will get the best possible model. So, okay, great. So now that you are well acquainted with cross-validation, or if you've acquired the superpower, it is very important to know how to use it, right? As the great philosopher Uncle Ben once spoke, with great power comes great responsibility. So how do we do cross-validation right? Let's consider the following scenario, right? We have data with many predictors. I don't know. My favorite example is still the genetics case, right? We have 20, 30, 80,000, whatever genes or other proteins or stuff like that. But essentially, I mean, if you take an image, you have, I don't know, 1,000 by 1,000 pixels, you also have quite a few possible predictors, right? So think of your favorite example. How do we normally go about this? How do we build a model? Well, we could, for example, select those predictors that have the strongest univariate, so one-to-one correlation with the output. Because if we really have 20 or 80,000 predictors, do we really want to work with all of them? Nah, not really. Okay, so now we have, let's say, the top 100 or so, the top, or however many such most strongly correlated predictors. We build a multivariate model on these predictors. Those are the ones that matter, right? And then we use cross-validation to tune the model parameters. what is the degree of the model and that kind of stuff, right? That's okay. Sounds good, right? I don't hear anybody object, but that may again have to do with that I'm not in a lecture hall. Let's assume that we get 50 samples, 2 balanced classes, right? 50 samples. And we have, let's say, 5,000 continuous valued Gaussian distributed predictors that are independent of the class labels. Okay, so A, we have very little data. B, we have 5,000 completely uninformative, essentially nonsense predictors, right? So what would the test error of any classifier on this data be? What is the true test error? 50-50. There is nothing to be learned from these predictors. So the best guess is just either this or that. It's 50-50. You can again think of the no classifier that we had in the previous lecture. You can take the yes classifier. You just toss a coin, 50-50. It's all going to be basically potato, right? Good. That's what we should have. Let's now think what happens when we actually do this. Let's build that model, right? Not that wall. Let's build that model. Let's say we choose 100 predictors in step 1. We use one nearest neighbors to classify on these predictors. And now we're going to evaluate what is the truth, or what is the test error. We're going to estimate the test error using cross-validation. Okay, and we do this 50 times. But what do we get? It's a bit surprising, because what we get is that the average test error is 3%. And it should be 50. So what, how, why, what is this? I don't even, but exactly. This doesn't make really sense. Because we have been doing cross-validation wrong. What was good was the idea to include cross-validation in the process, but how we did it was wrong. The predictors we chose over all of the data, that's where things went wrong. If we choose the most correlated predictors over all of the data, and then use cross-validation over some subset of the data, then in a way, the predictors we chose already have, or the process of choosing them already has some knowledge about the data we're going to be testing on. This is what we call leakage. We don't want our model to leak. So if we would have done it right, we would have done cross-validation first. Select the most correlated predictors on the training data, and then evaluate the test data. But we didn't. There was leakage. Well, we didn't immediately see this coming while I was explaining the slide. Well, of course, I'm very upset and bad, right? I mean, next time do better and all that, right? But you would not be the only one who does it wrong. You don't want to know how many papers that are even, like I'm reviewing recently, do this wrong. They have gotten the idea I need to use cross-validation, but they forget where to use it, how to use it. It's not just in research papers where people have pressure to publish, right? And maybe they get it wrong because they didn't have time to think about it. Maybe they wanted to fool people. Maybe both are bad, but not, well, it's now, is it, well, 16 years ago, I think. 16? Yeah, I think 16 years ago already. My God, I mean, that's of legal drinking age here in Germany. Fantastic. It was the Netflix challenge. Maybe you've heard of it, maybe you haven't. Netflix challenge was issued by Netflix. I mean, big surprise there. And essentially what they wanted to do, they wanted, given some training data over which videos, which movies, which things people, well, then it was really still renting, which of those, how can you use this information to predict what people are going to be watching soon, right? In order to improve the recommender system. Pretty neat idea. Use historic data to predict the future, make money, right? And ... profit. They offered $1 million for that person or that team that improved most by a certain deadline over their own recommender system. You can imagine that quite a few people tried their hand at this, right? Because 1 million US, right? I mean, well, actually these days it's even 1 million euro. It's almost on parity, sadly. I mean, sadly, because I'm currently, while you're listening to this, I'm in the US, and hence my euro doesn't buy as many dollars as it once did. But okay, that aside. Now, in that setup, I mean, many people flocked to it, and there were lots of proposals. I mean, not, and in the end, I mean, I forgot how strongly, but there was one team that really it blew the original Netflix recommended completely out of the water. Some complicated ensemble of methods and blah blah, and all sorts of words that you don't know yet, but by the end of EML, you will understand very well. And perhaps I'll repeat them by then. On the test data, perfect, did so well, right? And then they ran it in practice, and it turned out to be really, really bad. I mean, much worse than their own recommender system. So yeah, that was 1 million wasted. Why? Because the training data was leaky. What they did, if this is, let's say, well, these are users, right? As the rows are users, the columns are movies. Now, if I now select some of these movies, or for certain users, I select some movies that need to be predicted. Basically, I shoot a few holes in my metrics. And then I ask you to predict what are the values in those holes. For example, I want to predict if a certain user has watched Harry Potter 5, right? Well, normally, in a normal operation, would probably do this knowing that they either have or have not watched Harry Potter 1, 2, 3, 4, right? And then Harry Potter 5. And if they haven't watched 1, 2, 3, 4 in your system, there is a probability that they might want to see the 5th movie, maybe not, right? Now, suppose that I gave you also the information that they watched Harry Potter 1, 2, 3, 4, and I give you the information that they watched 6 and 7. Now, big question. Has this person watched Harry Potter 5? Well, yeah, there's leakage. There's leakage. I mean, you have, in a way, information from the future that normally you would never have. There are, of course, a few instances where people have watched the 4 movies, the first movies, and then the final movies. And then, for some weird reason, they choose to watch the 5th one, which up till then they've never watched. But yeah, come on, right? The task was leaky. There was information from the future in the training data. What they should have done is essentially take a snapshot of the data, train on that, and then in the future, take another snapshot, look at the difference, and predict those. Would have been the right thing, but yeah, oops. It was just $1 million at play. So don't feel too bad if you didn't immediately spot the error on this slide, right? People that, I'm not sure if they were fired for this, but I'm pretty sure they got a memo. Good. One other way of looking at the example I just gave on the previous slides is determining the correlation between the selected predictors to the output. Well, how would we do this wrong, right? For didactic reasons, I start with wrong. Select the 100 predictors that are most strongly correlated using all samples. This is where it goes wrong, right? We should not be using them. Now, if we now choose out of all now a random set of 10 samples, that's essentially what the wrong way of doing cross-validation is then all about. We can compute the correlations of those predictors in the output of just that, right? And we get something that looks like this. And you see that even though the data generating process is still the same, right? Nothing changed. So the bump should really be here, but you can see that, hey, there's a positive correlation. Yeah, this is because we selected those predictors over all data. So of course, it would be very strange if somehow we selected these 100 predictors that are most correlated over all samples, and then we managed to select randomly those 10 under which they are, well, not correlated. I mean, that's not going to happen. There's going to be a positive bias. So the mean here is 28%. Bad idea. The right way to do it is to start by dividing your data into k classes, k folds, right? And then for each of those, we train on the all folds except for the one that we leave out, right? For those, we find the predictors most correlated with the output. And then on the fold that we held out, we then see what is the actual correlation. That's what we should do. And that we do now, we repeat this k times. We accumulate all these errors, and look, then we have a plot that looks like this. In certain cases, yeah, we have negative correlation or positive, but the mean here is correct. This is how we estimate it. So always be very careful where to place your cross-validation loop, right? Pretty much as outward as you can. If you have multiple things that you want to estimate, there are parameters that are dependent on one each other. What should you do? You should nest cross-validation. You see this in a future slide, right? So the most important thing is we have a multi-step procedure. You have to apply cross-validation to each of the steps, each of the steps in the sequence, or at least the entire sequence of steps. Okay, so like I said, if we have now things that are dependent on one another, what we need is not just a validation set approach, which cross-validation is an instance of. We need an instance of the train validation test paradigm. The concept is not covered, if I recall correctly, in ISLR, but it's so simple that I do want to cover it. And there's also a few paragraphs that's in the ESL book. What we do now is we take the data we're given and we split it into 3 parts. We have a training part, like we've seen before. This is how we're going to be fitting models. We have then a second part, for example, 25%, to validate which of these trained models are actually best. And then we use the test set to evaluate the performance of that model. Basically, all the choices we have, right? So in blue, we have choices, which parameters do we choose? In green, it's like, which model do we choose, right? Which is the best set of parameters. And then we're going to see on, again, fresh data, how well does this model do? Now, this is in a way the best that you can do, right? So, and of course, if you want to fit multiple dependent parameters, then you need to have perhaps multiple of the training and validation steps, but the test set should really be kept separate. Now, with this multiple, what we're actually doing, we have a form of nested cross-validation, where what you first do is optimize your hyperparameters, for example, the how many parameters do you have, right? And then in the this is the wait a second. No, in the inner here, we tune the parameters, and in the outer loop, where we keep apart the light green stuff, that's the data we're going to be using to test those tuned parameters, the tuned models, right? Okay, there we are. Now, just like, because this is an instance of this train, test, validate, or train, validate, test paradigm, this will give you more conservative error estimates than normal cross-validation does. So basically, we're not going to underestimate, it's going to be more conservative. It's hopefully going to be closer to the truth. However, by nesting this cross-validation, we are, of course, now, let's look at the top one, we leave here this part out for the test set. So we're only training on 4 out of 6 blocks. Well, are we? No, because what we're actually doing, we're doing the tuning over 3 blocks, evaluating internally 3 blocks in order to determine which are the best set of parameters. And that is now, so we are shrinking our data quite a bit. So unless we have quite a lot of data, we would be suffering from the bias variance trade-off. So buyer beware. Good. That was it for cross-validation. I have one more goodie for you today. Cross-validation is a superpower, but it's not the only superpower that I'm going to give you today. The next superpower I'm going to discuss with you is the bootstrap. And I have to admit that I had heard of bootstrap back when I was doing my PhD and even the first few years of postdoc and as a professor. Only until I started teaching EML, I actually, well, I had to teach it, so I had to read up on it and like, okay, but wait a second, this is a superpower. This is really, really cool. Why wasn't I, well, told that this is as important as it is? And I still don't really know. I can't explain it, but I am now going to share the superpower with you. Chapters 5.2, respectively 7.11 in ISLR and ESL. Whereas cross-validation is useful to estimate test error, bootstrap can give you an estimate of how uncertain we are about a certain parameter, or we can quantify the uncertainty of a given estimator. So in linear regression, we didn't really need that, right? We already saw that we can analytically theoretically determine what is now the confidence interval of a certain parameter, whatnot. But there's plenty of cases out there, even though we haven't seen many of them, where, yeah, not as clear, right? For example, LDA, QDA, it's linear-ish, but it's not really linear regression. So, okay, how would we estimate how strong are, how certain are we about the parameter or the coefficient estimates? Bootstrap is the tool for that. And it's not just a tool for that, it's a type of mindset, a type of thinking that is actually the brilliance behind it. Okay, let's give an example. I mean, we want to be rich. Who doesn't want to be rich, right? We're going to be starting small. We're going to invest a certain amount of money, let's say 100 euros or something like that. And we can't really make our minds up whether we should invest in X or in Y. So what do? We invest a bit in both. And that is smart because we are hedging our bets, right? That's essentially how hedge funds make their money, by not going all in on one thing, but you want to spread your risks. Okay, so we have 100 euros. We're going to spend a certain fraction alpha into X, and then, well, the rest, 1 minus alpha into Y. Now, of course, our goal is to choose alpha such that we minimize our risk of losing money. Essentially maximizing the risk that we make money while minimizing that we are also bankrupt. So what we want to do is we want to choose alpha, minimizing the risk, the variance of the overall investment. What is the variance of alpha times X plus 1 minus alpha Y. Okay, now we can break this apart. What is alpha then? Alpha should be, if we minimize this, the variance of Y minus the joint variance over the variance of X, variance of Y minus. Okay, what do we have here? This is the covariance Y. Okay. What does this mean? This means that if we now want to choose alpha optimally, this is how we should choose it, we would have to base it on the variances of X and Y, respectively covariance, which we would have to estimate. Okay, so the best estimate that we have is alpha hat looks like this, these estimates. Okay, fine, right? Let's see. Suppose that I here now have 4, but I could many more times, right? I get 100 data points for the same message, right? I mean, I can sort of go back in time machine, change one little thingy, something like this. We have slightly different dependencies, slightly different, situations, right? Where it would have been smart or bad to invest in X and Y. So essentially, for each of those situations, for each of these 100 data points, we would estimate a different alpha, right? Each of those, we have a different variance of X, different variance of Y, different covariance, right? For each of those. So in all of those, we would get a slightly different alpha. Now, suppose we're not going to do this just for 4 cases. We're going to do this 1,000 times. We're going to have not one, but we're going to have 1,000 estimates for alpha, right? Where basically it's going to look like this. Here we have them. Oh, did this as some homework preparing for this lecture. These are the number of cases, and this is the value of alpha. I mean, we discretized alpha a little bit. As you can see, the true value, that's the dotted line over here. Perfect, right? So if we have 1,000 independently drawn data sets, right, all from the same distribution, we can actually estimate the true alpha. These are here, by the way, the true values. Ignore this for now. However, this assumes that I can get new data sets, not just once, 1,000 independent ones. You could say, okay, well, hey, we just learned about cross-validation. We should just chop our data up. Let's chop our data up into 1,000 folds or parts, right? And on each of those, we're going to estimate alpha. And yeah, but how about bias and variance, right? It's such small data. I mean, what's going to happen? Yes, indeed. No, that's not a great idea. You should not minimize the data that much, right? So that's just going to drive up the variance. And this is the killer idea. This is really one of those like, wait, what? We can resample from the training data. What we're going to be doing is we have our training data. And what we're simply going to do is we're going to draw uniformly at random with replacement, that's the important part. With replacement, we're going to uniformly at random, with replacement, draw randomly a data set of n records. That's what we're going to do. So I have a new data set, but I used just my original training data set, right? My training data. And we're going to do it not once, not twice, but many, many times. In this particular case, 1,000. That's perhaps a bit over the top in practice, but it gets the image, it gets the message across. Now, each of those data sets are slightly different. And what is now the beauty is that it gives us an unbiased estimate of the uncertainty of your estimator. So the standard error is defined like this. Let's skip over that because I want to show this figure. What we have over here is that we have here on the left-hand side, this is the true distribution drawn here from the left. That's why it's also in blue. As you can see, we slightly underestimate alpha here, which is, well, basically because we chose this box, right? And that's or somewhere in this box. It's slightly left of the dashed line. And this is distribution. It's beautiful. If given just one sample from this data, not 1,000, just one, is more realistic to have. And just by resampling, like we do in Bootstrap, this is the distribution we have. This is the box plot. So the mean in this particular case is slightly underestimated. Well, if the true one is already slightly underestimated, okay, I'll allow it. As you can see, the true value is still within interquartile range. That is pretty neat. Distributions are very similar. And the nice thing is, we can't just do this for alpha in our in our investment example, right? In our get rich fast or die trying example. We can do this for any parameter. Just by taking our data set, randomly sampling with replacement and samples, running our method, doing this a number of times. The more often we do this, like I said, 1,000 is perhaps a bit over the top, but the more we do it, the better the bootstrap estimate of the uncertainty is going to be. Nice. Just give you a visual example of how does this work. Here we have a data set with a whopping 3 data points. Here it is. This is the original data set. And what we now do, we're going to draw bootstrap samples. And we're going to do this multiple times, right? So B times in total. So first time I draw uniformly at random, third record, there it is. Then uniformly at random, and I choose this one, Pikachu. Okay, there you are. And well, then I randomly choose 3 again. This is my data set over. Oops, back. This is my first data set. I do this multiple times, completely independently. And for each of those data sets, I get my estimates for alpha, and that's that. It's really, this is all there is to it. It's like ridiculously simple. Now, you might say, wait a second, these data sets, they will be very similar because we're drawing them all the time from the same data. So that sounds icky. That sounds icky. And yeah, you're right. It's not perfect, but hey, it does work. We just saw it, right? So if it works, it's not stupid, but we need to figure out how stupid is it or how great is it? What is the probability of a data point occurring into multiple bootstrap sets, or in multiple times in one bootstrap set, actually. That's more important. Multiple times. So basically, how often did I now choose record 3 in previous example, right? It's actually a very simple binomial because we're choosing uniformly at random, one out of n records, and we're doing this n times. So there we have it. 1 minus, there we have a binomial. We can approximate this roughly. It's 1 to e to the power minus 1. 63. 63%. 63% probability of drawing sample multiple times. What does this mean? This means if you now do this times n records in a training data where you have n records, on expectation, we're gonna draw 63% of the training data into our bootstrap set. There is roughly 1/3 of the data not included in the bootstrap set. And if we do this again, independently, we again draw 63% of the data. And there will be another third we don't use. There is some overlap between these things, right? So there is some correlation that we can't shake off. But 2/3, 1/3 is quite okay. What is actually nice about this is that by doing bootstrap this way, we know which data points we sampled. We can keep track of that. on expectation, 63%. Expectation, roughly 30, 36, 37% of the data points will be out of bag, as we call it, right? So bagging and boosting, these are two terms that are very related. We choose an element into the training bag, and the out of bag samples are the ones that are left unchosen. This gives us a very natural training and test set. In a way, you can think of the bootstrap as sort of a weird instantiation of threefold cross-validation, where we don't really have the two folds that we train on chosen explicitly, but hey, deal with that. Now, if you would use somehow to the in bag, the out of bag, wait a second, if we would evaluate on the in bag samples, we create an overlap, test and train, and then, well, the test error or whatever, the certainty that we assess is going to be way underestimated. So that we shouldn't do. So again, no leakage. Keep these two things apart. Also, know that this 63% on expectation, it might be that you are like, well, super lucky or unlucky in a way, and you choose exactly the training data set, right? So every record was chosen once. Okay, then you don't have any natural test set anymore. Something to keep in mind. Maybe you always want to keep part of your data separate over which you do not bootstrap. Keep that in mind. Okay, this is what I already said. Because there's a high overlap between bootstrap samples, there's an increase in the variance. There is some icky stuff going on, but overall, it's unbiased. That's nice. Good. I'm done. Actually, almost say that I like this online lecture. Actually, no, I missed you. I missed the interaction. That's why we're already done. The only thing I have left for you is the conclusion of the day. If we want to evaluate how well the model generalizes, what test error is, and so on and so forth, we have to test it on other data than it was trained on. And really other. Keep it separate. Keep it physically separate, right? No leakage allowed. What we've seen today are different approaches for what's called resampling or subsampling of the data. Because in both the validation set approach, what do? We have the data, we essentially sample two parts. In leave one out cross-validation, we basically, in a very deterministic way, we sample one test point and then the rest are the training point. In cross-validation, again, we sample bootstrap. We sample, essentially, this entire lecture could have been called resampling or subsampling, but that goes a bit beyond the point. It's a bit too much focusing on what we're doing it. And what we do is more of a, well, it's less interesting, let's say, than why we do it. The question why is way more interesting. Why do we do this? Well, we want to learn about the variability of a fitted model. Right? So if we have now different training sets, I mean, how much can I trust it? We want to be able to test or to assess the test error. How good is this method really? And with that, because we know that we typically underestimate the test error, what is often more important, we want to be able to choose what is the right complexity of the model. So once again, it's often reasonably easy to get more training data later on, and then it's just a matter of retraining, and there you are. Now, resampling, all the approaches we've seen today, they are brilliant. These are superpowers, right? Always use them. Always when you can. Because resampling is computationally expensive. Not so much the sampling itself, but for example, in cross-validation, like I said, let's do 10-fold cross-validation. That means we need to, in order to get a CV estimate of the error, we need to train 10 models, each on 90% of the data. Okay, well, training a model 10 times, that's already a lot. And I actually said, okay, well, you have to repeat this 10 times with independent random initializations of cross-validation. So it's like 100 training runs to get one number. For reasonably complicated models, there's computing power allows for this, right? I mean, with clusters, AWS, either on your phone. I mean, your phone is more powerful than whatever they had available when the book was written. However, in the meantime, we have stuff like deep learning, heavily over-parameterized methods that really require insane amounts of compute. If you see, for example, like all these fancy diffusion-based image generators, what are they trained on? They train on massive amounts of data, and it really takes weeks and weeks of GPU time to train a model once. So are we going to do cross-validation there? Are we going to train it 10 times, let alone 100 times? No. Ain't nobody got time for that. That we're definitely not going to do. So cross-validation is often not used for deep learning, which is problematic because especially for these highly over-parameterized models that do extremely well on their training data, maybe on one test set, but there you would really like to know how good are these test errors? Can we really trust this? Does it generalize? Yes or no? How important or how certain are we about the coefficients? I mean, is this like super brittle and we have to just get right, or like, okay, actually, no, it's just fine and it doesn't really matter so much. I mean, whatever may happen, my model is going to be fine. Those are exactly the questions you want to have answered for these overcomplicated methods or models. These are exactly the things that we cannot answer yet. So, and that indeed is currently still a big open research problem. So while you are watching this video, I'm walking around, talking with people, learning a lot about the latest research in machine learning at NeurIPS. And I am very much looking forward to hearing about the newest, latest, and greatest on exactly this topic. How can we assess the generalization power of these super powerful methods? Good. On that, I thank you for your attention. See you again in person next week. We're going to be talking about model selection beyond cross-validation. Bye-bye.